elc138 21. Now notice I am in the AC circuit book. So if I go back to the DC circuit book, then what we want to talk today about is inductors. Okay, magnetism and inductors. This gets into some calculus, so it's good for light reading. It's good for some of the answers on the worksheet, but it doesn't get into too much about inductors. So in the AC book, what we want to do is look at complex numbers, which is chapter 2, and you really want to get the feel for polar and rectangular notation. Okay, everything in AC is a vector, so he starts out with vectors in AC, and so everything in DC was a vector too, but everything in DC pointed in the same direction. So we didn't have to worry about the vector notation. In AC, we have vectors that are pointing in different directions. So in 2 dimensions, we need to think about them in terms of either a polar or rectangular notation. So you will want to go through this chapter a little bit. And then chapter 3, there's a fundamental equation that we want to get to, and you can read it or you can get there to it. This is the differential equation for voltage. I don't expect you to do differential equations because that would be calculus, but this is the equation that we will be most interested in. XL equals 2 pi times frequency times the inductance. That's the equation that we need for the worksheet. Now, in looking at the worksheet, name some common items that are inductive. So if you go through the inductive chapter, you can probably come up with some things that are inductive. How can a magnetic field be created immediately as needed? That answer is pretty straightforward. Don't overcomplicate it. What are magnetic devices used for? You can get a little bit into how is alternating voltage generated. I would just Google that. And how can alternating voltage levels be changed? I'm just looking for the device that changes it, which happens to be an inductive device. Okay. Now, 6 refers to the polar to rectangular that I pointed out earlier. You want to get to the point where you can go back and forth. The better you do this and the less struggle you have with it, the easier AC will just be. Okay. So, go through the chapter, come up with different ways, come up with a way that you can do it. In the AC class, if I teach it, I normally do a spreadsheet where we develop how to do it, and then we just put it in the spreadsheet where all you got to do is type in a number and poof, there's your answer. I don't know what will happen. I have certainly, well, we can certainly do that. What's the period of a waveform? We've been over that. How does it relate to frequency? This question keeps coming up because I want everybody to be getting it right every time. Okay? What is the inductive reactance of a 3 millihenry inductor at 60 hertz? Well, that goes back to our equation that I just showed you last. XL is inductive reactance, and inductance is in henries. Now, usually your inductance is going to be in millihenries, and this equation needs to be converted to henries, and you know what that means. And then there is your frequency, the frequency of the AC waveform. So what you see is for a given inductor of, say, inductance L, if the frequency varies, the inductive reactance will vary for a given inductor. And that's an important concept to sort of get used to. which is why I asked the question. So, what's the inductive reactance of a 3 millihenry at 60 hertz and then 60 k hertz? Now, you know the difference between hertz and k hertz, right? And so you would expect that inductive reactance to change. If an inductive reactance of value 2 ohms is in series with a resistor of value 10 ohms, what is the impedance? Okay. Now we're getting into the impedance, and I know he discusses it, and I'm just not 100% sure where. Yeah, reactance and impedance. So it's probably down there. No, I don't know. Okay. AC inductor circuits, AC resistor circuits. Okay, so here we go. Now, series inductor and resistor circuits. So if I have an AC source and I have a resistance and I have an inductance, then my resistance will behave in one direction, one vector direction. My inductance will behave in another vector direction. So the combination of resistor and inductor in series is a vector, and it's now called impedance. So you can have a resistance, you can have an inductance, and then the combination of the two becomes impedance. Now, technically speaking, impedance, if all you have is resistors, then your resistance is your impedance. If all you have is inductive reactance, then the inductive reactance is your impedance. But your impedance can contain both. Okay? Now, from the standpoint of, and he's got an example right here, but don't scroll down too fast. From the standpoint of adding a resistor to an inductor, here it is in polar form. Here it is in rectangular form. And what you see is my resistor will always be real. It will have no imaginary part in the rectangular form. And my inductor will only have the imaginary part and will have no real part. So if I add these two together, I'm just adding and making this number. So I've got a real part, I've got an imaginary part, and I can convert that to a vector. Okay? Or I can convert that to polar. So this is the polar form, which is equal to the rectangular form, and this is why I want y'all to look at that. Going back and forth. Okay, here it is as angles. Now your calculator may do this in angles. But it's not intuitively easy that you're going to add a 0 to a 90 and get 37 degrees. Okay? Just, that one's not easier. I like the rectangular because I know 5 and 3, I can graph that. Go out my x-axis 5, up my y-axis 3, 0.76 or 77. And then I've got two sides of a right triangle, and then this would just be the hypotenuse and the angle above the positive x-axis. So once you get that relationship established, it's pretty easy. Okay? That takes some work, and that takes some doing, and this is what we'll do in the AC class. What I want to do in this class is get you going between rectangular and polar and give you just a little bit of it up front so you know going into it. Okay, so if an inductive reactance of 2 ohms is in series with a resistor of 10 ohms, what is the impedance? Well, if you know the resistor is real and you know the inductive reactance is imaginary, then it would be this real part plus this imaginary part, and you could put it in the rectangular form. If an inductive reactance of 2 is in parallel with a resistor of 10, what is the impedance? Now, this is the same formula that we've had in the past. where you do the 1 over 1 over, except your inductive reactance will have the imaginary operator, the I or the J, whichever you choose to use, and you still have to come up with a common denominator. It's just a little more complicated of a problem. Okay? And he may have one of those in series. In parallel. Let's see what he does. There you go. Parallel resistor inductor networks. Okay? He's doing it a little bit different way than I do, but that's fine. What you want to learn is a way, and you want to be comfortable with it. Okay? So he's trying to stay away from that formula, I think. Yeah, there's the formula. So my resistance in parallel was all this, so now my impedance is the same. And so I can use this formula if I want to. So there is an example that he can sort of work through, and you should be able to get it. And then don't get too intimidated by these problems. I'm keeping them easy. These are just very, very basic. Just you gotta understand the concept, and then we'll build on that. That's why we're starting some of the AC concepts in the DC class, because you need a little more time on the AC stuff than you did on the DC stuff. Okay, so if I've got 2 ohms in parallel of 10 ohms, what's the impedance? Okay, so those are just polar, rectangular, and doing the equations, but now they're actually complex. You're actually using complex numbers. Needing an inductive reactance of 10 ohms at 60 hertz requires what inductance value? Now I'm back to the 2 pi FL equation. XL equals 2 pi FL. I'm just solving for a different variable. Needing an inductive reactance of 100 ohms at 600 hertz requires what inductance value? And you're going to notice something interesting about 12 and 13. So I'll let you find out what that is. Inductors do what? Now, resistors limit the flow of current in general. Okay, so you gotta be careful when you define resistors as resistors resist, because you're using the word to define itself, which is bad form. So resistors limit current always. Doesn't matter the direction. What happens with an inductor is they oppose changes in currents. So if my current is increasing, my inductor is opposed to that, opposed to increasing current. So it's going to act sort of like a resistance. Sort of. Not the same. When my current is actually decreasing, my inductor will try and oppose the decreasing current, which means it will try and boost the current, which is not what resistors ever do. So the safe thing to say is inductors oppose changes in current. Alright, now you got some understanding what they are. Now how to measure them. When reading an inductor with an ohm meter, what does the meter show? Well, once you know how an inductor is made, you will realize that it is something that should show some ohms, but it will not show the inductive reactance of that inductor. The only thing it will show is the ohms of the wire that it was made of. Now, ohming an inductor is a value because sometimes they open up, in which case they don't work anymore. And an ohm meter will tell you if your inductor has opened up, but it does not give you the inductive reactance. It does not. Got a typo here. What is 3 minus 8i in polar form? Should be form, not 4. So, again, this is a rectangular to polar conversion. What is the answer to 2 plus 3i times 6 minus 2i in polar form? So if you've ever done the FOIL method, you can multiply it out. You'll come up with a rectangular answer, and then you can convert it to polar. The key is that I squared is equal to -1. So your I squared terms become -1. If a 50 ohm resistor is added to a 30 ohm inductive reactance, what is the impedance? In both polar and rectangular form, so they are in series. And then complex conjugate. I didn't look up where he talks about it, but you can Google it. What is the complex conjugate? And I'm giving you a rectangular form, so you know how to turn any rectangular form and find the complex conjugate of a rectangular form. And what is the complex conjugate of a polar form? So I'm giving you a polar form and asking you what the complex conjugate is. This can be a little bit of an intimidating worksheet, but don't get too intense. This is just the start of an AC, and we're going to work with it. And I think the next worksheet we go back to some DC, and eventually we do some stuff with basic capacitance. But once you get the complex numbers, polar, rectangular, you start working with that a little bit. It's going to make AC so much easier. And that is this worksheet, worksheet 21. And I thank you for watching.